All right, guys. In Chapter 6, we're going to talk about samples and populations. So let's start by talking about what a sample is and what a population is and what the differences between them are. So the population is a group of a set of individuals that share at least one characteristic. A sample is a small number of individuals from the population. So generally, we're looking to research something about a population, but we certainly are not able to measure an entire population. We're limited by time and resources. So what sampling allows us to do is if we have sampled appropriately, we should be able to use that sample to draw conclusions about the larger population. So we call that being able to generalize. Can we take our results and apply them to the population? So even a well-designed project, will have errors, okay? And error will play a role in that. And as I mentioned before, criminal justice research is often flawed. Researchers can, however, anticipate and reduce errors to the point where it doesn't make our findings useless. So what are some sources of error? Well, what if we have taken a sample and we have sent out a survey to them and a large number of them refuse to cooperate, okay? If there is something very different, there could be something about that group that chose not to participate that there could be something about them that makes us unable to generalize to the population as a whole. We might fail to contact a segment of the populations. Respondents might not be candid and honest with us. So a lot of times people know what the socially desirable response is and they might provide that. They may misunderstand the question. And then there's also errors in data entry. Recall we were looking at some data in the NIBRS data where we found some offenders, right, who were like 1 year old, okay? That's obviously a data entry error. Okay, so one of the things we want to do is engage in random sampling whenever possible. A random sample means every member of the population has the same chance of being included. So say I wanted to draw some conclusions about Fisher College students, okay? When I draw my sample, I want to make sure that every single Fisher College student had the same chance of being included. So what we do then is we begin with a list of every member of that population. And we can get a random sample a couple different ways. We might use a table of random numbers. We might assign everybody a unique identifier, then enter the random number table at any number and move in any direction. So we might say, we're going to enter at this point. We're going to go every 5 respondents. Okay, now we can get even more specific with our types of random samples. The best type of random sample is a stratified random sample, okay? But those are a little harder to do. So we could be systematic, right? So we're going to pick every 5th person after choosing that random starting point. Now a stratified random sample is we're going to divide that group into several homogeneous subgroups, okay, or strata. So I could divide a group into their religious affiliation. I could divide them into social class. I could divide them based on race or gender, okay, and then draw random samples from the strata, okay. Now those strata are generally determined based on what type of variables are important for your study. We can also engage in what's called multistage sampling, and this is cluster sampling. The NCVS uses cluster sampling, okay? We use this to minimize the cost of a large survey. So what we do is we sample twice, okay? First, we have a primary sampling unit. So when we think about the NCVS, their sampling unit is households, okay? That's their final sampling unit. So we might say we're going to go by cities or census tracts, okay? And then within each city, we're going to sample from within that cluster, okay? So first we delineate clusters, okay, and we sample those, and then we sample from within those. Now, if you do that really well, you can use a relatively small sample and generalize your findings. So a simple random sample is similar to drawing numbers from a hat. Systemic means every whatever member is included, every 5th, every 7th. Stratified is going to divide the population into strata and then sample. And then a cluster sample, samples are drawn at different levels. Okay, so with sampling comes some sampling error. By chance alone, we can always expect some difference between a sample and the population from which it's drawn. Okay, so remember we've used some abbreviations before, and we're going to use different symbols for samples as opposed to population. Okay, so when we talk about the mean, in our sample, it's X bar, and in the population, it's mu. That's that funny looking M. Standard deviation in a sample is S, and in a population, it's sigma. The standard error in a sample is SX bar, and the standard error in a population is going to be sigma X bar. Sorry, that should be sigma mu. So even though this concept of sampling error might sound strange, you should be familiar with it. Okay, so think about an election. They'll report a poll, and they'll tell you usually a margin of error, plus or minus 3, plus or minus 5. Okay, so if they tell you 49% of people are going to vote for so-and-so, plus or minus 3, it really means that it's between, they're confident that it's between 46 and 52. Just had to do that math in my head. Okay, so that's the sample to which, the extent to which that sample mean can vary from the population due to sampling error, okay? We can't be certain of our results because of sampling error, right? We could make some mistake in the sample. Okay, now we're starting to get into the tougher things. Okay, now we're also going to talk about the sampling distribution of means. So this is a frequency distribution of a large number of random sample means that have been drawn from the same population. Okay, so imagine I have a population and I'm going to draw an infinite number of samples from that, right? What's the average of each sample? I should be able to plot those out on a distribution, okay? And it should look like the normal curve. Remember that bell curve, okay? The mean of the sample distribution of means, so remember we've got a population. Imagine I have 10 samples from that. Each sample has an average. The average of those averages is the actual mean of the population. Okay? And then the standard deviation of a sampling distribution of means is smaller than the standard deviation of the population. Okay? So there's our population distribution. That's our sample distribution. We have an observed sampling distribution and a theoretical sampling distribution for an infinite number of samples in the last one. Okay? We can also see this as a probability distribution. So you might recall we've got each standard deviation here, right? So we have mu, the average, and then plus 1 minus 1, plus 2 minus 2, plus 3 minus 3. Okay, so one of the things we want to often do when we get an average or a mean is we want to calculate a confidence interval, okay? So we rarely collect data on more than 1 or 2 samples. It's just not really feasible to collect multiple samples. So we generally don't know the mean of means or the standard deviation of the sampling distribution. Okay, but a standard deviation of a theoretical distribution can be determined, and that's called the standard error of the mean. We take the population standard deviation and divide it by the square root of the sample size. Okay? So remember, sigma x bar is the standard error of the mean. We get that by taking the population standard deviation, dividing it by the square root of the sample size, right? Remember, n is the number of respondents in the sample. So this distinction between standard deviation and standard error can be confusing. Standard deviation talks about, remember, we've got a set of scores, okay, and how they're distributed around the mean, okay? Standard error is the variability of a sample-based summary statistic, okay? So it reflects the extent to which it might diverge from mu. Okay, so take a random sample of cases, right? We don't know what mu is. We're going to use the sample mean as the best estimate of the population mean. Okay, but we could just as easily obtain one of these other samples of size n with its estimate of mu. Okay, so we've got this average, right? We have a mean. And what we want to do is kind of really delineate how confident we are. Okay, so we can calculate confidence intervals at different levels, although they're generally calculated at a 95%, sometimes 99%. Okay, so let's look at the middle one. 95% confidence interval is equal to X bar, right? So our sample mean plus and minus 1.96 sigma X bar. So let's look at that. Okay, as I mentioned, it's just a matter of convention. We use the 95% confidence interval. We're willing to generally accept that 5 times out of every 100 that we are wrong. Okay, now the greater our confidence level, the more confident we are that the population mean is within these two numbers, okay, the larger the z-score. Okay, the larger the margin of error, the wider the confidence interval. So it's pretty rare that we know the actual standard deviation of the population. So how do we calculate then the standard error of the mean? Well, we can estimate it, okay? So we're going to do an estimated standard error of the mean. I'm going to get that by taking the standard deviation of the sample, dividing it by the square root of n minus 1. You're going to see n minus 1 a lot. We might be tempted to substitute the sample standard deviation of the population, but this would underestimate the size of the true standard error. For any given sample drawn from a population, the sample variance and standard deviation are smaller when computed from the sample mean. So in order to correct for that, we divide by n minus 1 instead of n. There's two very different purposes for calculating variance and standard deviation. Okay, one is to describe the extent of variability within a sample of cases, and the other is to make an inference or generalize about the extent of variability within the larger population of cases from which a sample was drawn. So say we want to assess a new method of teaching, right? If the teacher is only concerned about her kids, she would use n. If she wants to be able to take that information and generalize it to a larger population of students, she needs to use n minus 1. One more problem arises when we estimate the standard error of the mean. The sampling distribution of means is no longer quite normal if we don't know the population standard error. So the fact that we estimate standard error from sample data adds an extra amount of uncertainty. The ratio follows what is known as the t-distribution, which is also called the student's distribution, and interestingly enough, was developed by beer makers. So we use the degrees of freedom to determine which t-distribution applies. Okay, degrees of freedom indicates how close the t-distribution comes to approximating the normal curve. So d of f, degrees of freedom, is n minus 1. The sample size minus 1. Larger the sample size, the greater the degrees of freedom, the closer the t-distribution gets to the normal distribution. As that happens, it starts to approach the z-score. So when we use the sample standard deviation and not the population standard deviation, the distribution is not normal. So remember, normal means it's a bell curve. Okay, so we have to use the t-distribution there. We can use table C to find the value of t. Okay, so let's look at this, right? With a step-by-step example, let's see how it translates into constructing confidence intervals. Suppose a criminal justice researcher wants to examine the number of security cameras in stores in a large shopping mall, and he selects a random sample of 10 stores. He goes into them and he counts the number of security cameras in each store. He gets 1, 5, 2, 3, 4, 1, 2, 2, 4, 3. Okay, so first we need to find the mean, right? We're going to add them all up and divide by n. Okay, the mean here is 2.7. Okay, so the mean of this actual group is 2.7. If we want to generalize that, right, we want to figure out what the population mean is, the mean for all the stores, we can do that with a 95% confidence interval. So now we got to get the standard deviation of the sample, which we've done before, and you could see here it's been done with the raw score formula. We're then going to calculate the estimated standard error of the mean. And then we're going to look at the t value of t. Okay, so when we look at t, we're looking for a critical value. Okay, so in this case, the degrees of freedom is n minus 1. So that's 9. Remember, there were 10 cameras in the sample, 10 stores in the sample. Okay, and we're setting alpha at 0.05. So t is 2.262. Okay, then we're going to get the margin of error by multiplying the estimated standard error of the mean by that t-score. Okay, and we're going to get 0.96. We add and subtract that from the sample mean to determine the interval within which we are 95% confident the population mean falls. So we are 95% sure that the average number of security cameras per store is between 1.74 and 3.66. Okay, what do we do when we have a large sample? Okay, so here we have a frequency distribution. Right, so 21 places have 1, 32 places have 2, right, for a sample size of 120. Sorry, this isn't camera. This is the average number of convictions amongst inmates in the state prison population. Okay, it's fairly skewed to the right. There's a small percentage of inmates with many convictions and a large percentage with fewer, okay? So it's not normally distributed, okay? But by virtue of the large sample size, the sampling distribution of X bar will be normal, okay? So we're going to use the t distribution here. So first we have to get the average. We're going to do like we did in prior chapters. Then we're going to again calculate the standard deviation of the sample. Calculate the estimated standard error of the mean. And then we're going to look up that critical value, okay? Now 119 degrees of freedom is not in table C, so we use the next available, which is 60. So the degrees of freedom, the critical value of T for 60 degrees of freedom and an alpha of 0.05 is 2.00. So we just need to see then. So we're going to take that, multiply it to determine our margin of error, and add and subtract it from the sample mean. So we are 95% certain that the average number of convictions for the entire population of state prison inmates is between 2.89 and 3.51. Now we can use the same thing to estimate proportions. Okay, so the only difference is that we're going to use the Z distribution as opposed to T. Okay, so we're going to take P, the sample proportion, and we're going to do plus or minus 1.96 S of P. Okay? And the standard error of the proportion is the square root of P times 1 minus P over N. Okay, so suppose we want to estimate the recidivism rate of inmates released from prison in a particular state. So we want to think about the percentage of ex-inmates who are arrested for a new felony within 3 years of their release from prison. Okay, we can't really follow up with every person who's been released. So we're going to randomly select 550 to investigate and determine that 341 members of the sample had recidivated within 3 years. Okay, so let's look at the 95% confidence interval for a proportion. So we're going to estimate the sample of the proportion. That's F divided by N, and in this case, that's 0.62. Okay, the standard error of the proportion is 0.62 times 1 minus 0.62 divided by 550 and take the square root. Okay, then we're going to take that number and multiply it by 1.96 plus or minus it to the point, then we're going to plus or minus it to P. Okay, so we are 95% confident. Sorry, we're working this one backwards. The researcher can then conclude with a 95% confident, that the population recidivism rate is roughly between 58%, 0.5793, and 66%, 0.6607. Okay, and that wraps up this chapter.